So we've got this idea that the universe gets trapped in a state of false vacuum and as a result for some brief period of time back when it was incredibly young expands absolutely like crazy. But how does this actually solve our three enigmas?
Well, let's start with the first one. The fact that if I look at two things on the sky, they have essentially the same temperature now. They seem almost exactly the same. The only way we know how to do that is for them to have been in contact in the past. So the problem is when we run the universe back, when this doesn't happen, you get a trajectory, and I take those 2 points, and boom, back at the time of the Big Bang here at t equals 0, they're still separated. They never had a chance to get together and talk to each other. Now let's think of a universe that exponentially expands. So that's one which is kind of minding its own business, and suddenly goes, woo! So instead of being extrapolated back here, it means you've given the universe the time to literally go and get together. And so at a finite amount of time, the two objects are right next to each other so they can be at the same temperature. So that's a good start.
Yes, so the bits of the universe are much closer together out here than we would otherwise expected, which allows them to actually merge. And then during the expansion, they were expanding faster than light. You might think nothing can travel faster than light, but actually nothing's moving. It's just being carried apart by the motion of space. So in fact, they can travel faster than light if it's space doing all the work. And so that carries them apart to their current distances where they cannot contact each other, but they could have been in contact in the past. So that's nice. Okay.
Yeah, okay, so there's one thing.
Tick.
So let's think about the next one.
So curvature.
Yeah.
The idea here was that we know that the universe is fairly close to being flat. We're not sure how close yet. But if it was curved, either it was a spherical universe or a saddle-shaped universe, it should get more and more curved or more saddle-shaped as time goes on. And so by now, even a very small deviation at the beginning should have amplified into enormously small or enormously curved one way or the other. And in fact, we know it's pretty close to flat at the moment.
But if we exponentially expand the universe, you're going to take a curved piece of universe and you're going to make it really, really big. And so suddenly that still looks a little curved, but not as curved as before. Now imagine magnifying that by 60 orders of magnitude, which is what we think may have happened in the early universe. Then that idea is you make a circle bigger and bigger. You can actually, on a computer, for example, make it out of straight lines. Well, our little part of the universe, the curvature will look like a straight line. It will look flat.
You take any shape you like, no matter how curved, and you expand it by 60 orders of magnitude, and any bit you can see locally is going to look pretty flat after that.
Yeah, it's sort of like the Earth, actually. This is why people think the Earth's flat. At least some people do, because it looks flat to them locally.
Okay, so that's another tick. It solves this problem. How about the origin of the lumps that make the universe have galaxies?
Start a random universe off. You don't end up with this map of how galaxies make this cosmic foam. So if you're expanding exponentially, something by 60 orders of magnitude, then you're going to take something smaller than an atom and expand it to the size of the universe.
But we know that on scales smaller than atom, space is not smooth because of quantum mechanical fluctuations. Right. We talked about this a little bit in the very first course in the series, that so-called empty space isn't really empty. You've got particle and antiparticle pairs spontaneously appearing and disappearing. And this sounds like fantasy, but it's actually quite measurable in our laboratories. And in fact, it's being tested every day on labs around here at the ANU. So the idea would be that these tiny quantum fluctuations that happen to be happening just at the moment when inflation took off would get stretched enormously. And so a fluctuation that might have been the size of an electron ends up forming a supercluster of galaxies today.
And one of the interesting things is normally if you think of Paul and I as being a set of quantum fluctuations, and you'll be real matter and I'll be anti or whatever, we are formed, but because the universe is exponentially expanding in that very tiny period of time allowed by the Heisenberg uncertainty principle, we've expanded so much that now we're further than the speed of light can connect us.
So we can never recombine.
So we can never recombine. We become suddenly real particles, not virtual particles, real particles. And that's what we think made the bumps and wiggles in the universe. They're amplified particles that have been created to be huge. And it turns out you get a very specific white noise look to what the bumps and wiggles should look like. And that's exactly what we need to make the patterns of galaxies.
It's so-called scale-free spectrum. Means there's equal amounts of lumpiness on every scale from very small up to very large. There is one problem here. Before we give this a big tick, it does predict that there should be fluctuations. It says they come from quantum mechanics, and it predicts that the relative amount of big and small ones should be the same, but the amplitude is completely arbitrary.
Yeah.
It could predict that these fluctuations are a billion times bigger, so everything would collapse to form a black hole a nanosecond after the Big Bang, or a billion times smaller, in which case nothing would ever have formed. That all depends on the crucial exact shape of this Mexican hat, which isn't really a firm prediction from the theory. So it gets the spectrum right and the existence right, but there's still a bit of a fudge factor in there for actually getting the right size of these fluctuations.
But it does get ticks from a very skeptical person here who was around before the structure of galaxies were measured. It got that right in advance. And before the curvature of the universe was measured, got that right in advance. And indeed, I thought the universe had curvature when I was studying it as a graduate student. Turns out it doesn't have much, just like this theory predicted.
So that's a good theory, a theory that can actually predict things ahead of time.
Yeah.
It's all too easy to come up with a theory after the event that explains things. Politicians do that all the time. But actually be able to predict something before it happens, that's a good sign.